What do you see here? Yes, it is a circle inside a cube. Are you familiar with the problems of packing spheres inside a box? This is a different problem which lends itself to utilizing topics from Calculus 3 to engineer. With the recent advent of Desmos 3D, I thought it might be interesting to make one of the first videos explaining some of its features through solving a hard problem. This is problem B3 on the 2008 Putnam exam. What is the largest possible radius of a circle contained in a four-dimensional hypercube of side length 1? Instead of doing this problem for the 4D cube, we will jump down a dimension and do it for the more concrete problem of a 3D cube. In particular, we will engineer it into Desmos 3D. Case 1. The simplest case of the circle embedded inside the cube would be where it is contained in one of its faces. Then the radius would be 1/2. Case 2. This plane slice constructed from the equation y plus z equals 0 is a rectangle with a width of 1/2, so the radius of the circle inside will also be 1/2. You can see the circle lying in the xy plane. We would like to rotate the circle upward so that it lies within the rectangle. But how do we make this happen? The big idea is to think like a mechanical engineer. This is how I think about mathematics. Rather than static symbols on a page, I think of math as dynamic in terms of physics and mechanics. We would like to rotate all the points on the circle about the x-axis. In physics, we call this line the axis of rotation. It is like a hinge on a door. Each point can be parametrically described by the usual polar coordinates. This is the map we need to invent. When I first started solving this problem, this is the animation I had envisioned. The levers are fixed at a point on the x-axis and rotate up, making a certain angle with the ground. The levers represent the initial y values. Then as the levers lift up, the z component also changes. Once we analyze this movement, we can construct the map. One key thing to note is that the x-coordinate stays fixed. It does not change. I was so elated when the program I wrote in Desmos 3D worked one early morning before going to my job. I had scribbled this picture in my notebook and finally made it come to life on the screen. When the levers rotate up by an angle alpha from the xy plane, we get this right triangle diagram. The initial point is x, y, 0, and the final point is x prime, y prime, z prime, which is what we are trying to find. The red part is y, so the hypotenuse of the triangle is also y, which is r sine t. The blue leg is z prime, and the red leg is y prime. Using simple right triangle trigonometry, we discover the new coordinate functions. X prime equals x, y prime equals r cosine alpha sine t, and z prime equals r sine alpha sine t. And this is the final map we can program into Desmos. Here we have our plane, y plus z equals 0. We want to know the angle alpha it makes with the xy plane. Since the long edge is the diagonal of the square face, the angle below is 45 degrees. Since the faces are parallel, alpha will also be 45 degrees. There is one important thing to note, however. We are rotating in the opposite direction. Therefore, we would enter negative 45 degrees into our rotation function. Here is the result after all our hard work. A rhombus through the center of the cube running along the main diagonal is another polygon we might imagine. The one we have here is given by the equation 1/2 x plus 1/2 y plus z equals 0. We want to inscribe a circle, but it seems more difficult this time. Here is why. The angle the rhombus makes with the xy plane is not 45 degrees. Additionally, the axis of rotation is not the x-axis. It is the line y equals minus x. How do we rotate the circle properly? First, let's find the angle alpha. We simply draw the main diagonal inside the cube and extract the right triangle. The length of the two legs are square root 2 and 1. Thus, tangent alpha equals 1 over square root 2. And yes, despite what you have maybe been taught, it is okay to divide by a square root. Using a calculator, we find alpha is approximately 35.3 degrees. Now, of course, as mentioned earlier, you might see a little problem. The axis of rotation is not the x-axis. It looks like the plane has been rotated 45 degrees clockwise, or negative 45 degrees. How can we accomplish this extra rotation? There is a matrix that rotates any point in the xy plane about the origin for any angle. This is given by little r of theta as seen here. Then we plug in minus pi over 4 and multiply the column vector of only the xy coordinates of our previous rotation function. This matrix gives the negative 45-degree twist. Here is the twist in action. We will not go over how to find the radius of the circle, as that is contained in my book, Learning Isn't Linear. Here is our final map to program in. We have our angle, the radius of the circle, and the plane. There is one last thing I forgot to mention earlier. We need to check that the x, y, and z components of our rotation function obey the plane equation. We will use the form x plus y equals 2z. Then plugging in, we obtain this equation. We see that we can cancel the r's and cancel the sine t's. After this, we have the simplified equation. Now divide by 2 and divide by cosine alpha. This results in tangent alpha equals square root 2 over 2. Now take tangent inverse of both sides, obtaining our familiar angle. And since all the steps are reversible, this means that the circle will be inscribed in the rhombus. Programming this into Desmos, here is the result of all our hard work. Here is the backstory to the conception of this video. I saw a post on Facebook about Desmos 3D and clicked on the link to try it. After creating a sphere, I put in a random plane equation, x plus y equals z. The plane curiously intersected the cube in the face of a hexagon, and immediately it reminded me of the 2008 Putnam problem I had mentioned in Learning Isn't Linear. From that moment, I believed I could engineer the solution into Desmos. Our claim is that the circle with the largest radius lies within this regular hexagon that goes through the center of the cube. And we claim that the plane x plus y minus z equals 0 slices through the cube, producing this hexagon. Now we want to calculate the angle alpha for the hexagon plane. Given the plane x plus y minus z equals 0, this immediately deconstructs into the dot product of a general point and the normal to the plane. We will want to find the angle between the normal vector and the vector in the xy plane. This is given by the formula a dot b equals the magnitude of a times the magnitude of b times cosine theta, where theta is the angle between the two vectors a and b. The vector we will choose as b will be minus 1, minus 1, 0. You will see why we have chosen this in a second. We will construct this hexagon by putting the vertices as the midpoints of 6 of the edges of the cube. We will then take 2 of those points and the origin and construct the plane by calculating what would be the normal to the plane. If the normal turns out to be some scalar factor of the vector 1, 1, minus 1, then we are done. We find the normal vector to the plane by computing the cross product of the vectors A and B. When we do this, we get A cross B equals 1/4, 1, 1, minus 1, which is what we wanted to show. Now you might point out that the normal vector should be in the opposite direction. This is true, but I wanted to make it more clear on the picture, and it makes no difference whether it is negative or positive, and it is just a scalar factor. It seems the only things left to do are find the angle alpha the hexagon plane makes with the xy plane and the radius of the circle inscribed inside the regular hexagon. We find the radius by solving for the length of an edge of the hexagon. On the diagram, we make an isosceles right triangle with legs of 1/2 each, and so the diagonal is square root 2/2. The rest is a standard problem in geometry to find the radius to be square root 6/4. The red vector is a normal to the plane, the green vector is b, and the angle between them is theta. Normal means perpendicular to the plane. And we have our angle alpha. The sum of the angles is 180 degrees. Solving for alpha, we obtain the equation. Now we can finally calculate alpha. Using the dot product formula, we have the following equation, which reduces to 2 equals square root 6 cosine theta. Upon dividing by square root 6 and taking cosine inverse, we obtain theta equals cosine inverse of 2/radical 6. After subtracting from 90 degrees, we obtain alpha is approximately 54.7 degrees. Here is the product of our patience and perseverance. Now an important question might come to mind. How do we know the regular hexagonal plane x plus y equals z does in fact contain the largest circle inside the cube? What about an octagon? Well, we know the circle must go through the center of the cube, so this eliminates a lot of possibilities. Here's an animation that illustrates the answer to this question. The animation continuously deforms into all possible planes. You can see where it reaches the optimization point and then starts shrinking. Now it's time to celebrate. If you enjoyed watching this video, hit the like and subscribe button now. And yes, I did finally realize I could have just used b cross a instead of a cross b to get rid of the negative on the normal vector. It has to do with that right-hand rule thingamajig. And remember, life is tough, so let's prioritize long-term learning over short-term test taking.